So our function of z is written u plus iv, where u is a function of x and y and v is a function of x and y. Now the first Cauchy-Riemann equation says that du dx equals dv dy. U comes before v, just like in the alphabet, and x comes before y in the alphabet. To get the second Cauchy-Riemann equation, we interchange x and y, and we change the sign of one of the derivatives. So du dx becomes du dy, dv dy becomes dv dx, and I put a minus sign in front of this one, or in front of this one. Let's suppose that we differentiate partially with respect to x, du dy. That can be written d2u dx dy. Now we can apply a Cauchy-Riemann equation here, replace du dy with minus dv dx, and we get minus the second partial derivative of v with respect to x. So that's du dy. What about the partial with respect to y of du dx? Well, we can replace du dx with dv dy, and we end up getting the second partial of v with respect to y. But these two derivatives are the same, provided our function u is well behaved. So these are the same, and if they're the same, we get this result here, which is Laplace's equation. So if f of z is analytic, the Cauchy-Riemann equations follow, and Laplace's equation follows. So this holds for the function u. We can also show that the function v will work as well. To show this, let's look at the second partial derivative of v with respect to x. Well, we can write it like this, and we can use a Cauchy-Riemann equation to replace dv dx. So we'll use this second equation here. dv dx is minus du dy. So we get minus the second partial derivative of u with respect to xy dx dy. Let's look at this here. d2v dy2, that can be written d dy of dv dy. Let's replace dv dy. If we go back up here, we can replace it with du dx. We don't have any minus sign here. So now we can see that this here is just minus this quantity here. So in other words, this quantity here, which is just the same as this here, is minus this quantity here. So this quantity is just d2v dx2 is equal to minus this quantity. And from that result we get this second Laplace equation. If fz is an analytic function, then the functions u and v are called conjugate harmonic functions. Let's suppose that u is given by x times y. Let's show that it satisfies Laplace's equation. Well, the partial derivative of u with respect to x is just y, because we treat y as a constant when we take this derivative. So u is just a constant times x, so differentiating with respect to x gives us just that constant. Du dy is got by treating x as a constant. Now we need the second derivatives. That's going to be 0, and the second derivative of u with respect to y is also 0, since we're treating x as a constant when taking this derivative. So this is Laplace's equation, and clearly we get 0 plus 0 equals 0. So Laplace's equation is satisfied by the function u equals xy. Now we want to find the conjugate harmonic function v, such that our function f of z is an analytic function. So we must satisfy the Cauchy-Riemann equations. So here's the first Cauchy-Riemann equation: du dx equals dv dy. Well, we got du dx, we know that it's equal to y. So we want dv dy to equal y. So we want the partial derivative of some function v with respect to y to equal y. So that means v must have the form of half y squared plus a, because if we differentiate this with respect to y, we get y, and then we have a function of x added onto a half y squared. If we differentiate a function of x with respect to y, we get 0. So we just integrated this, but now the constant of integration is a function of x, because the partial derivative of a function of x with respect to y is 0. Now let's look at the second Cauchy-Riemann equation. We interchange x and y here and change the sign of one of the derivatives. Now du dy, as we saw, is x. Since dv dx equals minus du dy, we have dv dx equals minus x. So we have to integrate minus x with respect to x, and that's going to give us minus half x squared plus a function of y. So the constant of integration is a function of y. If we differentiate a function of y with respect to x, we get 0. So here's another form that v can have, but of course the two of them must be the same. So we want dv dy to equal y, so a half y squared has to appear in our expression for v, and we want dv dx to be minus x, so minus a half x squared must also appear in it. So we just add them together and we get a half into y squared minus x squared. So we add a half y squared onto minus a half x squared. Now we also have a constant. Now this is just a number, it's not a function of x or y. So we see that we could have left v in this form here, so our function of x, this part here, is actually minus a half x squared. Or if we use this form here, our function of y, this part of it, must be half y squared. Well, plus or minus a number, that number is c. Well, when we pool the numbers we get c. So now we can write down our function f of z. We were given u at the start, it's xy, and we found v. Well, v is multiplied by I, so half y squared minus x squared times I, and then we have c times I. Well, c times I is just a constant, which we can call d. So d is just a complex number. It's actually just ci, where c is some number. We can actually write our function like this here. Z squared, well, z, remember, is x plus iy. And if we square that out, well, let's just do that. We get x squared, squaring this term. When we square this term here, we get I squared y squared, that's minus y squared. And the imaginary term is 2xyi. So, if we work this out, you'll see that it will all check out. We just have to get half of all of this and add on d. Let's look at this function here, u equals x squared minus x minus y squared. We want to show that u is harmonic. That means we want to show that it satisfies Laplace's equation. So we take the first derivative, that's 2x minus 1, first derivative with respect to x. The second derivative just gives us 2. We need the first derivative of u with respect to y, that's minus 2y. And the second derivative of u with respect to y is minus 2. And we get 2 plus minus 2 equals 0. Next we are going to get the conjugate harmonic function v. Now the Cauchy-Riemann equations tell us that du dx is equal to dv dy. So to find v, we integrate this with respect to y. So we treat 2x and minus 1 as constants. We get 2x minus y, and then we must have a function of x. So if we differentiate a function of x with respect to y, we get 0. Now the other Cauchy-Riemann equation tells us that du dy equals minus dv dx, or dv dx equals plus 2y. We negate this term. We integrate 2y with respect to x, so y is treated as a constant, so we get a function of y here. So we see that v must contain 2xy, this term, if we want dv dy to have the term 2x, and it must contain minus y if we want dv dy to be minus 1. Also, if v contains the term 2xy, dv dx will be plus 2y. So the 2xy takes care of both of these. So basically we just put these together, but we ignore the duplication. So the 2xy just appears once, and we have a constant c, that's just a number. That number c could be a complex number, it doesn't have to be a purely real number. Next we are going to write down f of z. Well, we were given u, Here's u, x squared minus x minus y squared. And we found v. Now v is multiplied by I, so we 2xyi minus I times y, and then we c times I. Well, that's just a number, so we just call that d. Now notice that x squared minus y squared plus 2xyi is the same as x plus iy all squared. If we square out x plus iy, we get x squared minus y squared plus 2xyi, and what's left in is minus x minus iy. Well, that's just minus all of this, that's just minus z. So we can actually write all of this here as z squared minus z plus d, where z is x plus iy.